All right, welcome back to The Explainer. Today, we are absolutely cracking open a fascinating game of microscopic building blocks. I really want you to think of today's topic like a giant molecular Lego puzzle. We're diving deep into the concept of isomerism, and honestly, it's this wild phenomenon that shows us just how incredibly versatile and clever nature can be at the microscopic level. So if you're the kind of learner who loves seeing how things fit together, you're going to absolutely love what we're looking at today. Let's get into it.
Here's our roadmap for this journey. We'll start with Part 1, the Organic Chemistry Foundation. Then, Part 2, Unlocking the Isomerism Puzzle. Part 3 covers structural isomers, different connections. And finally, Part 4, Stereoisomers, exploring 3D space.
So let's kick things off with Section 1, the Organic Chemistry Foundation. Okay, to really grasp isomerism, we first have to ground ourselves in organic chemistry. Now, this is the scientific study of the structure, properties, and reactions of matter that contains carbon atoms. And let's be real, carbon is the undisputed star of the show here. The study of its structure means using all sorts of physical and chemical methods to figure out the exact composition of these organic compounds. Literally every single thing we're talking about today revolves around the incredible flexibility of the carbon atom. And that basic fact, that perfectly sets up our foundation to solve the main puzzle.
Which brings us to Section 2. Unlocking the isomerism puzzle.
So here's the big mystery. How is it possible that a collection of identical parts can build entirely different things? Let's define it. Isomerism happens when organic compounds have the exact same molecular formula, but entirely different structures or arrangements of carbon atoms inside them. I want you to really lean into that molecular Lego metaphor for a second. Just because you have the exact same number of red, blue, and yellow bricks doesn't mean you have to build the exact same house, right? You can take a set formula of atoms and just snap them together in vastly different configurations.
Now, check out this classification tree. It brilliantly shows us how isomers are divided up. At the very top, we've got isomers, but then, boom, we split into two main branches. On one side, we have structural isomerism, which is basically all about flat, 2D connections. It's how the atoms are literally wired together. Then, on the other side, we have stereoisomerism, which deals with how those atoms are arranged in 3D space. We're going to tackle that first branch, the structural side, right now.
Moving right along to Section 3, structural isomers, different connections.
So we are going to look really closely at how atoms are physically wired and linked up to create brand new structures. Structural isomerism actually breaks down into 6 distinct types. Ready? We've got chain isomerism, positional isomerism, functional isomerism, ring chain isomerism, metamerism isomerism, and tautomerism isomerism. Let's do a really fast-paced visual breakdown of each one of these.
Let's kick it off with chain isomerism. Take a look at these two compounds. They both share the exact same molecular formula, C4H10. But look at the carbon chain itself. In butane, the carbon atoms form a simple, straight horizontal line. But then in 2-methylpropane, the carbon chain is branched. It's like one of the carbons just popped off the end and attached itself right to the middle. Same exact formula, but an entirely different chain shape.
Next up is positional isomerism, and this one brilliantly illustrates how just slightly shifting a functional group changes the entire identity of the molecule. Take butene, for example. In but1-ene, the double bond between the carbons is sitting in the very first position, but in but2-ene, that double bond is just shifted right over into the second position, directly in the middle. The carbon skeleton hasn't changed its branching at all, but the position of that functional double bond absolutely has.
Okay, things get even more drastic with functional isomerism. Here, the exact same molecular formula represents two compounds that differ in the actual nature of their functional group. Take C3H6O2. In one arrangement, it forms propanoic acid, featuring an acid group right at the end. But in the other arrangement, those exact same atoms rearrange themselves so completely that they form methyl ethanoate, which has an ester linkage right smack in the middle of the chain. Same atoms, totally different chemical nature. Crazy, right?
Another super fascinating variation is metamerism isomerism. I want you to focus on the central oxygen atom in these structures. Metamerism is all about the nature of the alkyl groups attached on either side of that functional group. With diethyl ether, we have 2 carbons on the left and 2 carbons on the right, a perfectly symmetric split. But with methyl propyl ether, we only have 1 carbon on the left of the oxygen and 3 on the right. The alkyl groups literally shifted their weight around, creating a metameritical isomer.
Now check out this dramatic leap. This is ring chain isomerism.
Here, the isomers differ in the mode of linkage of the carbon atoms, specifically whether they form an open chain or a closed ring. Take propene. It's an open chain with a double bond. But those exact same atoms can literally snap together into a closed triangular loop to form cyclopropane. I mean, it's fascinating how the exact same molecular building blocks can build both a straight line and a closed geometric shape.
And finally, we arrive at the sixth structural type, tautomerism, isomerism. Now, the crucial point here is that tautomerism isn't static like the examples we just looked at. No, these compounds exist in a continuous, dynamic equilibrium with each other. Look at nitroethane and isonitroethane. The molecule is constantly shifting back and forth between a nitro form and an acy form. The atoms are literally migrating back and forth within the molecule itself. It's constantly in motion. And well, that covers the structural side of our roadmap, the 2D flat connections.
So, let's jump into Section 4, Stereoisomers, Exploring 3D Space.
We are officially stepping off the flat piece of paper and entering the three-dimensional world, where geometry is literally everything. I want you to think about this. What if the molecular connections are perfectly identical, like carbon A is absolutely attached to carbon B in both versions, but only the 3D space around them changes? Can they really be considered different molecules?
Well, the answer is a resounding yes, and that brings us to the definition of stereoisomerism. This is a type of isomerism where molecules have the exact same connections but differ entirely in the spatial arrangement of their atoms or groups. The physical blueprint of connections is exactly the same, but the way those atoms project out into 3D space is totally different. This mind-bending concept is our gateway to the two final types of isomers, geometrical and optical.
First up is geometrical isomerism. This is all about the spatial arrangement of atoms or groups around a rigid carbon-to-carbon double bond. In one setup, the two CH3 groups are locked on the exact same side of the double bond. This is called a cis isomer, specifically cis-2-butene. But if those exact same groups are locked on opposite, diagonal sides of the double bond, that is called a trans isomer, or trans-2-butene. Same connections, completely different spatial geometry.
Now, optical isomerism is visually stunning. Look at D-alanine and L-alanine. They are perfect mirror reflections of each other. But because of their 3D shape, you can never slide them over each other and have them perfectly overlap. They're what we call non-superimposable. Actually, it's exactly like your left and right hands. Your hands are perfect mirror images, right? But you literally can't perfectly stack your left hand on top of your right hand while they're facing the same way. It just doesn't work. And of course, we have a very specific scientific word for this phenomenon. Optical isomers, which are non-superimposable mirror images of each other, are called enantiomers. I really want you to anchor this complex 3D visual concept of the hands and mirrors to that specific name, enantiomers.
We've seen just how incredible the microscopic world is today, moving from basic structural chains all the way up to perfect 3D mirror images. So, as we wrap up this explainer, I want to leave you with a thought about the real-world biological power of these invisible geometric shapes. Think about this. How might a tiny spatial flip at the microscopic level, like a left-handed enantiomer versus a right-handed one, completely alter how a molecule interacts with the receptors in the human body? Just let that sink in for a bit. Let it fuel your curiosity until next time. Keep learning, keep exploring, and thanks for joining us.